In this video, we'll take a look at notes for section 11.1, inference about two population proportions. So in previous chapters, we've compared one proportion to a given value. In this chapter, or this section, we're going to take a look at two different samples and comparing them. So the first thing we want to be able to do is distinguish between independent and dependent sampling. So a sampling method is independent when an individual selected for one sample does not dictate which individual is to be in a second sample. A sampling method is dependent when an individual selected to be in one sample is used to determine the individual of the second sample. So dependent are usually matched pairs. So in this case, we're going to look at independent samples. So we're going to test hypotheses regarding two proportions from independent samples. So the first step is always to make sure that your requirements are met. By that I mean in this first box right here, these bulleted points, these are the requirements to make sure that we can use this hypothesis test method. So we want to make sure to test a hypothesis regarding two population proportions, population 1 and population 2, use the steps that follow, provided that the samples are independently obtained using simple random sampling or a completely randomized experiment. So that's the first requirement. It must be random. Second requirement is N1 times p hat 1 times 1 minus p hat 1 has to be greater than or equal to 10, and the same for N2 p hat 2 and 1 minus p hat 2. So the p hats, remember, are the sample proportions from each of your samples. Then the next requirement is N1 has to be less than or equal to 0.05, capital N1, and N2 less than or equal to 0.05, capital N2. What this means is the sample size is no more than 5% of the population size. This requirement ensures independence necessary for the binomial experiment. So proportions are binomials. Then we're going to determine the null and alternative hypothesis. So notice the null hypothesis this time is P1 is equal to P2. So we're seeing if the population proportions are equal to each other. Then the alternative is the same as in previous chapters. They're either not equal to, less than, or greater than. All right, so the p-value approach, we're not going to do calculate the test statistic by hand, but I included the formula if you want to take a look at it. We're going to use technology. So let's take a look at our example. Let me make this a little bit bigger so you can see it. So the problem we're going to look at, in clinical trials of Nasonex, 3,774 adult and adolescent allergy patients, patients 12 years and older, were randomly divided into two groups. The patients in group 1, the experimental group, received 200 units of Nasonex, or micrograms, while the patients in group 2, the control group, received a placebo. Of the 2,103 patients in the experimental group, 547 reported headaches as a side effect. Of the 1,671 patients in the control group, 368 reported headaches as a side effect. Is there significant evidence to conclude that the proportion of Nasonex users who experience headaches as a side effect is greater than the proportion in the control group at the 5% level of significance? So what we want to do is identify what our two samples are. So sample 1, we're going to let sample 1 equal the group that received Nasonex. In that sample, your X1 is 547, N1 is 2103. Sample 2 is going to be the group that received a placebo. So the X2, 368, and N2, 1671. So the X's refer to the number of people that had a headache. The N refers to the total number in each sample. Notice this is a completely randomized design. The response variable is whether or not the patient reports a headache. The treatments are the drugs, Nasonex or a placebo, and the subjects are the 3,774 adult and adolescent allergy patients. We're attempting to determine if the evidence suggests that the proportion of patients who report a headache and are receiving Nasonex is greater than the proportion of patients who report a headache and are receiving a placebo. So that's important to identify sample 1, sample 2. We have to verify the requirements are met. First requirement is random. They're both random. This is a randomized experiment, placebo group or the drug group. Then you have to check that each of these requirements met. These mean the sample size is large enough. So substitute your values. P1, P hat 1 is dividing your x1 divided by n1. So about 0.260. So 26% of patients reported a headache. In P hat 2, 22% reported a headache. Substitute your values in and make sure that both of those are greater than or equal to 10. The third requirement is the sample size is no more than 5% of the population size, and there's not a formula for this. It's a reasoning. The samples are less than 5% of the population of allergy sufferers in the United States. There's far more allergy sufferers than the 3,000 some that are in this experiment. So now we want to set up the null and alternative hypotheses. Null hypotheses, notice the notation, proportion 1, population proportion 1 equals population proportion 2. Versus, we think that is the proportion of patients taking Nasonex who experience a headache greater than the proportion of patients taking the placebo who experience a headache. So our alternative hypothesis is population 1 is greater than, population proportion 1 is greater than population proportion 2. So if you're trying to see if they're equal to each other or one is greater than the other, or think about it in terms of the differences between the two. Either the difference is 0 or the difference is greater than 0, depending on what our null and alternative hypothesis is. The significance level provided is 0.05. So here's how we're going to use the calculator. So we're going to use technology. So using the calculator, we want stats over to tests. This is a 2 proportion z-test, so we're comparing 2 proportions to each other. So on this calculator, it's option number 6, a 2-prop z-test. What the calculator needs are the values for your first and second samples. So x1 is 547. That's the number of people that had a headache taking Nasonex. N1 is 2103. So that's the actual number of people in that experiment. X2 are the number of people who experienced a headache, 368. N2 are the number of people taking the placebo, 1671. Then we want to know if P1 is greater than P2. So we write in the calculator P1 greater than P2, and then we calculate. So it gives us the z-score, which is 2.839, and it gives us a p-value of 0.00226. Okay, so that's using the calculator. If you're using StatCrunch, let me bring StatCrunch over. If you're using StatCrunch, let me make it a little smaller here. You're looking at, make it a little bigger for, there we go. We're going to do statistics, proportion statistics. This is 2 sample with a summary. So we type in the same items that we typed in the calculator. The number of successes, 547. In population 1, number of observations, 2103. Type in number of successes, 368, in your second population, over 1671. We are running a hypothesis test. Now the difference, P1 minus P2 is equal to 0, so this writes it a little bit different. The alternative is greater than 0. So this is the same place we do the confidence interval. compute, we should get exactly the same thing. We've got our z-score of 2.839 and our p-value of 0.0023. Okay, so that's how you use both the calculator and StatCrunch. Step 4, we're going to reject the null hypothesis because the p-value of 0.002 is less than the significance level of 0.05. So what does that mean? That means yes, there is evidence to show that the proportion of individuals 12 years and older taking the Nasonex who experience headaches is greater than the proportion of individuals 12 years and older taking the placebo. So then that's taking the test. The next thing we're going to do is construct a confidence interval for the same situation. The requirements are the same as the two proportion test. We'll use the previous example to construct and interpret a confidence interval. So if you're constructing a confidence interval that matches the hypothesis test, this hypothesis test was one-tailed, then the confidence level is 100% minus 2 times alpha, so we want a 90% confidence interval. So in the calculator, let me clear, stat over to tests. This is a 2 proportion z interval. So arrow down until you get 2 proportion z interval. There we go, 2 proportion z interval. It has the values recorded already from the previous entry. Our confidence level is 90%. Calculate. We end up with 0.01695 or about 0.017 to 0.0628 or 0.063. So our interpretation is we're 90% confident that the difference in the proportion of people who experienced headaches after taking Nasonex and a placebo is between 0.017 and 0.063. Notice that this supports our conclusion in the hypothesis test because the entire interval is greater than 0. If the difference is 0, then 0 would be included in the interval. So the confidence interval contains values greater than 0, which supports, again, the proportion of people who experience headaches after using Nasonex is greater than the proportion of people who experience headaches after taking a placebo. So using StatCrunch, we go back to the same place, stat, proportion stats, 2 samples with summary. You have to type it in again. 547, 2103, number of successes, 368, 1671. This time we want a confidence interval, and you have to put the confidence level in. Compute, and we get the same thing we did with the calculator, about 0.017, 0.063.